Hi all, welcome to this video in the supply chain analytics class. Today we're going to be talking about gravity location models in this video. Um, Gravity location models, so if you've read uh, through chapter 5, the first few sections of chapter 5, you'd have known that the design of supply chains essentially happens in 4 phases. We talked about phase 2, capacitated plant location model before, and in the capacitated plant location model, you decide where to locate your plant, where to locate your facilities, given a potential set of facility locations and your demand locations. Now, let's say that you want to figure out where to locate um, potential locations for intermediate facilities like warehouses. So let's say that you have supply coming in from some place, and then you want to consolidate all your supply in a single location, and then transport that supply from a single location to your demand locations. Where would you what is the best location for that intermediate location, or what's the best location for that warehouse? And one way to accomplish this is to use something called the gravity location model, which boils down to, if you remember high school physics, something like finding the center of gravity of your flow model. So a few things to keep in mind here. We need to know where your supply. We need to use this model. We need to know where the supply locations are. We need to know where the demand locations are. And once we know that, we also need to know how much supply do you expect from each supply location, and what kind of demand do you expect at each of the demand locations. And you also need to have a certain idea of the cost of shipping to to demand locations and from supply locations. So once you have that, what we're going to do is we're going to find the distance. So we are going to figure out the XY coordinate of the intermediate facility, and we're going to do this by figuring out the distance between the XY coordinate of the intermediate facility, the warehouse facility, and the supply locations, and the distance between the XY coordinate of the intermediate facility and the demand locations. We're going to find the distance using the coordinate geometry distance formula. It's a difference between the x coordinate squared plus the difference between the y coordinate squared under square root. So we're going to find the distance. Using the distance, we're going to find the total cost of shipping, and we're going to minimize the total cost of shipping. And that's what this model is going to be like. So here, let's take an example. So in this example, we have 3 supply sources, and we have 5 demand locations. The supply sources are Buffalo, Memphis, and St. Louis. And the demand locations are Atlanta, Boston, Jacksonville, Philadelphia, and New York. Now, a few things that you'll notice is that for each of these locations, you have a x and a y coordinate. Now, here we are assuming that everything is on a 2-dimensional plane, which is not exactly true, given that we are on a oblate sphere, which is the Earth. But and the distances here are large enough that the spherical nature of Earth does come into play. But for our approximate calculations, we're not going to worry about being on a sphere. We'll assume that it is relatively flat, at least within the United States. Now, the x coordinate for Buffalo is 700. The y coordinate for Buffalo is 1200. And you will notice that for Boston, again, the x coordinate is 1050 and the y coordinate is 1200. Y coordinate is essentially the height, and x coordinate is the distance from the x axis. So I think we are, you can see that approximately the origin is somewhere in California, approximately. That's how these numbers have been calculated. Apart from that, we know the cost of transportation and the quantity. So we expect the Buffalo source to send us 500 tons, the Memphis source to send us about 300 tons, and St. Louis to send us 700 tons. And the cost of transportation is 90 cents from Buffalo to wherever we locate our into warehouse. Memphis is 95 cents and St. Louis is 85 cents. Now the transportation from The warehouse to all the different market locations is fixed. It's $1.50. This is the data that's given. It doesn't have to be the same number. It can be any number. The total transportation cost is the cost per ton mile times the number of tons times the distance traveled. The cost per ton mile and the quantity, these numbers we already know. What's unknown is the distance. So how do we calculate? How do we figure out what the best value is? So what I'm going to do is I'm going to shift over to Excel. This data that we have here, I have this in Excel right here. So we're going to use Excel to figure out our answers. Okay, so I'm going to make this full screen bigger. All right. So let's say that let's call it the warehouse location. Let's say this is the X coordinate for the warehouse location. Call this X, X and Y. So this is the X and the Y coordinate for the warehouse location. I'm just gonna, as usual, I like coloring what I need to decide. So these are my decision variables. Now here we are going to calculate the distance. And this is the distance between the warehouse and each of these locations, the supply locations and the market locations. So let's calculate this distance. Right, so as we know, the distance formula is the coordinate geometry distance formula. It's a difference between the X coordinate square plus the difference between the Y coordinate square times all of this under square root. And so let's calculate. So what we're going to do is we're going to calculate the distance between Buffalo and our potential warehouse location, and calculate the distance between Memphis and our potential warehouse location. Now again, we are going to put this into solver to find the best coordinate for X and Y, the best values for X and Y. For the time being, I'm just going to leave it empty. So the distance is, so remember, it is X, the difference between X and X coordinates squared, plus the difference between the Y coordinates squared, right? Now all of this was under square root, so I guess the square root has to come first. Square root of all of that. So it's square root of the difference between the X coordinate square, difference between the Y coordinate square. Again, the warehouse location is the same, and I'm going to find the distance between the warehouse location and all of the other locations. So my warehouse location, I'm going to make that an absolute reference. I'm going to make that $E, $12, $12. So the distance here is distance between the warehouse and Buffalo, and this is the distance between warehouse and Memphis, and so on. Oh, oops. Right? Right. So now obviously these distances have been calculated assuming that the warehouse X and the Y coordinates are essentially 0. When you leave them empty, all these calculations are done assuming that they are zeros, but obviously they are not. Now, once you have these distances, we can now find the total cost of transportation. The total cost of transportation, as you remember, total cost of transportation is the distance times the quantity that is transported times the cost per ton mile. So this is cost per ton per mile. The cost of transporting 1 ton of materials 1 mile, that's 90 cents. So for Buffalo, 95 cents for Memphis, and so on. So the total cost will be the value of Fn times the value of Dn times the value of distance. So you're going to multiply these three numbers, multiply these three numbers, multiply the three numbers, and add them. So what we are essentially doing is a sum product. So we're going to do sum product. Now we've used sum product before, but only with two arrays. You don't have to do that. We can do sum product with multiple arrays. So we're going to do sum product of the f values, the d values, and the distance values. You can do sum product of three arrays, where again it's going to multiply 0.9 with 500 with this distance. To that it's going to add 0.95 times 300 times this distance, 0.85 times 700 times this distance. We're going to multiply all the corresponding values and then add them up, which is exactly what we want. And this is the total cost function. The total cost is here again. This is assuming that x and y are 0 and 0, but that's obviously not the case. So the only thing left is to put this into Excel and solve this problem. So we go to solver. The objective is the total cost, obviously, and you want to minimize the total cost. The decision variables, the cells, the changing variable cells are the x and the y coordinates. Those are the only values that are unknown. Now make sure that this remains GRG nonlinear. This is a nonlinear programming problem. This is a nonlinear optimization problem because our formula for distance is square root and a square and all of that. So this is obviously a nonlinear problem. It's not a linear problem. So now here we don't have any constraints. There are absolutely no constraints in this problem. Just the objective function is to minimize the total cost by changing the values of x and y. So what are the best values of x and y which minimize the total cost? So remember, the total cost function is we are multiplying the corresponding numbers and adding them up. So with this, the only thing left is to click on solve, and voila, that's the answer. I'm just gonna, for the sake of brevity, I'm gonna get rid of the decimals. Alright, so based on this, the x coordinate for the warehouse location is 681 and the y coordinate for warehouse location is 882. That's 681 comma 882. So 681, so Atlanta has an x coordinate of 600. So 681 is slightly to the east of Atlanta, and 882 is St. Louis, y coordinate of St. Louis, and it is slightly north of St. Louis, I would say that, right? So it's north of St. Louis on the y axis and east of Atlanta on the x axis. So where would that be? Let's see. Do we have it here? No, not at all. Okay, that's fine. And of course, the total cost is also here. That's the total cost. Now, don't forget to remember that this is a cost minimization problem and not a profit maximization problem. It's important to remember that. And the cost of this whole transport is about $1.265 million. And that's the cheapest you can do. And the x coordinate is 681 and the y coordinate is 882. That's a gravity location model. Very simple model, straightforward model, which considers flow from supply locations to warehouse and flow from warehouse to the market locations, and the amount of quantity, the quantity that flows, the cost of flow, and of course the distance. Now, one of the problematic parts of this model is that the distance is calculated as straight line distance between two locations. Obviously, when goods flow between different locations, they don't flow along straight lines. They flow along existing roadways or existing train lines or existing flight paths or airports and things like that. So those things have not been considered, but this is again an approximate model which you can use to figure out where the center of gravity of your flow model is. And in this case, it turns out to be x coordinate 681 and y coordinate 882. And that's where you have it.